things that went into it, and I decided that I was going to build my own very simple version of it. And so that is why I did that. However, my objectives were to make sure that I didn't.
Did you do this before you started working there, or after?
After. This is yes. This is a project that was inspired by them. And by the way, this is a super informal talk. You guys have any questions? Feel free to interrupt. I'm not, no big deal. So yeah, afterwards is when I was inspired to try this out. A big part of it also was that I had access, or I have access to a lot of the scientists that have done this already. So it's nice to be able to kind of tap into that resource and talk to them and say, hey, running into this issue, what do you think, or which direction should I go? The other thing is that, so anyway, I'll get into that stuff later. But yeah, so the limitations that I had were low cost, because I need money for my kids and time for my kids. Got 3 kids, a little difficult to do. So that was the whole purpose of this project. I could have gone out and bought, some super expensive and fancy stuff, but it was part of the challenge to try to see how much I could, how frugal I could be. So I will put together, I've put together on these slides some of the dollar amounts of what I've spent, kind of a running total. First thing is the drive. It's a tank tread robot, as you can see. You can buy this off of AliExpress for like $40. Diff drive, and the reason I chose this was because of those quadrature encoders. Each one of the motors has a 2-phase quadrature encoder that will give you feedback as to how much the shaft has spun, right? Every time and which direction. Every time the shaft spins, the ticks will happen, and you collect that. So that was a big selling point for me. I needed something that had encoders. The chassis I designed in FreeCAD myself, and it's open source. If you go to Thingiverse, you can download and print it yourself. It fits on top of this tank tread robot nicely. It's got some holes for screws and whatnot. Printed on my cheap little 3D printer, about $10 worth PLA. And then the motor controllers. So this is where sort of the metal meets the road. The motor controllers are necessary for 2 things, not just to drive the motors, but also to grab the encoder ticks. So I've got an Arduino Nano and this motor driver. And this driver, which is $5, and the Nano I got super cheap, 3 for $11. This driver is what takes the high voltage, high current, and drives the motors through a pulse width modulation pin that is driven off of the Nano. And then the other 2 pins off the motors from the encoders also plug into the Nano. And so I wrote a little bit of code on there that communicates with what I'll call the high-level software. As the motors tick, it'll drive an interrupt on the Nano, and that Nano will keep track of how many ticks have passed and in which direction. And also the Nano is able to receive information from the high level that gives it a basic steering command, like turn left or turn right or forward or backwards, right? So that's the purpose of these Nanos, and there's 2 of them because there's 2 motors. 2 Nanos, 2 motor drivers, 1 for each motor. And then, like I said, pulse width modulation control from the Nano to the driver, and so the memory on the Nano is actually being used for that purpose. Now, comms. This thing hooks up to the high-level board, which I'll talk to you about in a minute, via USB. And the high-level board sends it commands via basic UART, USB communication. And this thing returns back the encoder values and a particular timestamp. So the way that I designed it was also inspired by how we do things at work. There's a safety sort of protocol where you want to make sure that if you don't hear from the high level, you're not stuck in like a forward or a spin or whatever. So there's a minimum duration that you have to send with each command. So you can send it, go forward, and you can go forward at most like 70 milliseconds. And if this thing doesn't hear back from you in 70 milliseconds with the second command, then it stops. So let's see, the LiDAR. This is the critical piece that I need for mapping. The whole idea behind this is that I can drive this robot around a particular room, and using the LiDAR, I'll be able to map the environment and be able to see where the walls are, where the doors are, how big they are, so on and so So for that, we need this LiDAR. Cheap by LiDAR standards, $80 on eBay. It was produced originally for a vacuum cleaner, like a Roomba competitor, you know, just off the ground, and in fact you can get them nowadays too, just very, very nicely done vacuum cleaners that do exactly what I described using this LiDAR. It's not a fast LiDAR, but it's pretty good. And the protocol has been reverse engineered, so there's actually websites out there that you can go and you can see what the protocol is. It sends out data constantly, there's no receiving. All it does when you turn it on, starts spinning, collecting ranges, and sending that data out. So in order to communicate with this, I tried to do it directly off the high-level board, but it didn't work out well, so I ended up having to use this Arduino Mega.
What's the baud rate? Is it a serial port? Or?
It's a serial port, yeah. Yeah,
What's the baud rate?
115.2, yeah, kbps. So.
Do you have a range and a resolution on the LiDAR?
Yeah, the range is about 4 meters, 4.096 meters, so 4096 millimeters. And the resolution is 1 degree. So 360 degrees, one degree is per each range. So
How fast does it spin?
5 times a second.
5 times a second.
So
Okay.
it's pretty slow, as
Yeah.
you will see, but you know, it does the job. It does the job. So yeah, the reason I chose this Mega is because I needed 2 serial ports, and Mega has like 3 or 4, I think. One to get data off of this, and another to then via the USB go back to the high level and report back.
So for the Nito LiDAR,
Yeah.
are those basically being unassembled from
Yes,
vacuum cleaners? Or
they're
are
being
they-
salvaged.
okay.
Yeah.
Oh,
yeah.
really?
Yeah, they're salvaged off of these vacuum cleaners that people no longer, and they're very popular.
So you
Yeah.
can only get them on eBay? Or?
Yeah, pretty much.
Okay.
Yeah. No, we're going real cheap, man. Real cheap. You know,
Yeah.
nothing. No new parts.
Like an OEM manufacturer.
Yeah, no, unfortunately not. But I have heard of like brand new ones that are very, very similar to this. So it makes me wonder if it's the same Chinese manufacturer. For like $200, you can get something like brand new, and probably the next generation is a little bit better and faster. But this is basically all it is a rangefinder that is spinning, right? Laser rangefinder. It spins. It's a little bit of math that goes with it, but it spins certain directions. One shoots out the ray, the other, there's like a receiver on the other end, and then you do some calculations and you end up getting polar coordinates, right? A range and an angle, right? And then on the Mega, what I'm doing is I'm taking the LiDAR scans that are coming in and storing them in a memory map, basically, on the Mega with timestamps as to when those slices came in. And then I can tell, from the high level, I can tell the LiDAR or the Mega to say, give me this particular slice that I'm interested in, you know? And it goes through, and it basically asks the LiDAR almost continuously to give me the whole 360 view. But as time goes on, and I might want to be interested more in like a critical piece that's in front of the robot or to the side of the robot, I could sample that more frequently from the Mega. So.
Are the coordinates from the LiDAR, are those output in floating point format or fixed point?
The coordinates are not. The coordinates are just integers,
Integer,
per
yeah.
1 degree, right?
Right.
So you have 360, and then you have the millimeter range, right?
Okay.
Which is also an integer.
Okay, all right.
Right? So you have the range at this angle, and then you have to convert it to Cartesian off
Do you have a
board.
vertical beam width of the LiDAR?
The vertical beam width?
Yeah, it's gonna see a certain, each pulse that goes out is gonna see a vertical beam width.
No, it's one
What
plane.
does it say? One plane?
Sweeps one plane. That's
Okay.
it. Just
Just-
yeah, one plane. Yeah, it'd be cool. That would be a depth camera, right?
Well,
Where you could have
Not
the,
necessarily.
yeah.
It would just detect things that were, you know.
or you could twist the LiDAR, I guess, this way.
No, it just,
I've-
I work with sonar and it
Okay.
makes a difference on what the vertical beam width is and which gonna detect.
No, the LiDAR is just a tiny
It's a narrow
laser.
beam,
Yeah, it's you know.
It's just a
Yeah,
circular
just a
map.
circle. Yeah. So let me show you. This is it right here. If everyone can see, one of them shoots out the beam. One circle shoots out the beam. The other receives it. In fact, let me turn it on. You'll see.
You gonna blind?
Uh-oh.
Are you gonna blind
Oh,
it?
do I have batteries?
Uh-oh.
No. Hey, there it is. The demo effect, right? that's pretty much how it, you know, yeah. Just one plane is all it's got. So okay, so that's the
You're gonna
LiDAR.
run down your battery.
Oh, I've got plenty of battery. So, yeah, I was just kidding. I made sure I had enough battery. Okay, so did I tell you I work for a robotics company? Brain Corporation used to create these boards before they pivoted their business and they went towards a different direction with this floor scrubber. And so I just happened to join at the right time and they were thrown away, a couple hundred of these boards. And here I am, right? I got these boards. These are cool little boards, man. I couldn't believe that they were throwing it away, but they said, hey, this is no longer a business. I've got 3 USB ports on this side and another USB OTG on the other side, micro HDMI. It runs Linux, Ubuntu 12.04, so it's kind of an older, yeah.
Did they consider selling the boards?
They considered it, but then they decided it'd be too much effort to go and try to find buyers. So they donated a whole bunch to universities, they sent a lot off overseas, you know.
Well, didn't they try to sell the board for a while? I mean, that was kind of like...
I mean, if they sell the boards, they have to support the boards.
Yeah.
That's a problem.
Yeah, yeah. And they tried, but then in the end they're like, just get rid of it, we need the space. And us workers were there to pick up the scraps and sort of, so if anybody wants one of these boards, I could probably get you one, no problem. Anyway, I also inherited the battery, 3.3 amp hour battery, which is really nice, and by some happy accident, like I said, fit into the chassis. I didn't actually measure it out properly, but it worked.
That's not a LiPo battery.
It is.
It is?
Yeah,
Okay.
yeah. And then, yeah, this is, you can do binocular vision on this. They did a lot of research on binocular vision, and they designed this board specifically for that. So you can see on there, there's, I've got these 2 cameras right here, right, that just snap right into the board, which I'm hoping to be able to do some sort of binocular vision and matching with what the LiDAR is seeing and what the binocular vision is coming back
What
with.
software development tools?
So it's standard 1204 Linux, GCC, Make, you know, whatever, you know, anything that's a standard tool chain on Linux you can get on this. A lot of things you have to compile, like I compiled OpenCV 3.3 from source onto the ARM. It's an ARM board, right? It's a Qualcomm Snapdragon, so ARM architecture. But yeah, so that was free.
Okay.
Speaking of cost. So here's the high-level software that I'm using. These are some of the dependencies I'm using. Like I said, OpenCV 3.3, Boost, Eigen for the linear algebra. I'm using Hypodermic for dependency injection. That's a really neat thing. I highly recommend it. SQLite for the database that's on board, which is amazingly fast, and Rapid JSON for the communication with the UI to be able to control it. And then for external dependencies, just real old school, Apache and Fast CGI. I don't know how many people remember back in the 90s that Fast CGI was a thing. A lot of times though, people use ROS and Node.js, but because my purpose was to be able to learn and do these algorithms by hand and be able to really have a deep understanding, I opted to have as few dependencies as possible. You know, pretty much nothing that's involved with any kind of SLAM, anything localization or mapping wise. I wanted to force myself to learn and write it myself. So, and that will be part of another lecture. Here's kind of a screenshot of what the UI looks like. This is the LiDAR scan, and I'll show you, I should have this up on the Wi-Fi here shortly, and I'll be able to show you this in real time. But yeah, essentially, these 360 points is my workstation at home, you know, the room that's in there. This is probably about, I don't know, maybe a 10, maybe like 7 meters, 7 or 8 meters. Like it's almost at the range of the LiDAR. And then so this is the UI that I developed in HTML5 using this thing called Foria, which is kind of cool. It does 3D visualizations. I used to create the image, like create a PNG image and stream it to the web browser, but it was too slow. The vSem board couldn't handle the processing power needed to generate a board and then an image and then send it up via Wi-Fi. So what I ended up doing was sending the scans as a JSON string, and then on the browser rendering this image that you see here, and it made it a lot faster. So Challenges. I spoke a little bit about this. Snapdragon CPU is slow. Dual core helps a little. GPU support is limited. The only GPU support I get is if I wanted to do H.264 encoding, and that's a very high latency, so I can't get live feeds out of it, which is kind of a bummer. You know, on a Raspberry Pi, you could do a motion JPEG streaming, really nice. You know, it comes out with maybe a sub 200 millisecond latency, so it's pretty cool. Hey, Darren, Luis. These are my fellow colleagues from work, and also Darren is a Robotics Club member. Some of you might know.
Been here a couple times.
Yeah. Anyway, I/O, the internal SD card is kind of slow, and the Wi-Fi cuts out intermittently. So if in the middle of the demo it goes out, you'll know why.
Is that a problem on the Snapdragon?
In this particular board, yes. Yeah, it's a problem. I think it has to do with the Bluetooth Wi-Fi drivers that Qualcomm wrote in. Yeah.
So back the last slide, that image that you had,
Yeah.
is that taken, it's navigated around and that's sort of the reconstructed image of the space, or that's from
Correct.
a single position?
It's from a single position, sorry.
Okay.
That is a single LiDAR scan. So the idea is that I'll take those scans, I'll do the scan matching, I'll do, you know, basically SLAM and be able to create a map from multiple scans, just like we do at work. So.
And odometry.
And odometry, yes. Yes, it has, with the encoders, exactly. And I'm using legacy software. GCC 4.9 is the only thing I could really get on there, and Ubuntu 12. So not a lot of packages are pre-built. I ended up having to, like I said, compile things from scratch. OpenCV 3.3 took a day to compile. So the algorithms are the thing, though. You know, everything else up to that point you can kind of work around. The algorithms are the most important thing. This is the high math. You need a lot of knowledge for drift drive control systems. There's a guy at work that I talked to about that. That's his specialty. You know, PID tuning. You know, because each of those motors has a different characteristic.
Right.
When you send the same voltage through it, first of all, it'll never be the same. Second of all, one of them will always invariably go slower than the other, so the robot will start to veer, and you need to compensate. And just everything that goes into that is much deeper than I had anticipated. This is the noises that you get also from the encoders. It's not always, you know, depending on what surface you're on, depending on the amount of friction that, or the alignment of those tank
Your
treads.
wheels can slip.
Yeah, all
That
sorts
sort
of issues, yeah. So using Kalman filters, actually Kalman is misspelled. Supervised learning, these are things that I'm trying out to try to manage all of that. And then scan matching for the LiDARs. Yes?
Is the odometry done by the wheels turning?
Correct.
Or not
Yes.
a gyroscope, right?
It is not done by gyroscope right now, no. I'm just using the steering encoders.
So if you had different size wheels, you'd have to adjust it?
Well, you would just use different units. You know, you would calibrate it for that, but yes.
Okay.
Yes, correct.
Do you have encoders?
I have encoders.
Cool.
Yeah. So yeah, that's another operation. So in about 6 weeks, I'm planning on doing part 2 of this, and hopefully by then I will have all of this stuff figured out and be able to present something a little bit more.
So what exactly is the scan matching?
So scan matching is when, imagine you have a scan off of your LiDAR, right? It looks a certain way, and then the robot moves. And now you get another scan. Now most of that scan is similar to the one you had 2 steps ago. And what you want to do is to be able to match features within that scan, between those 2 scans, to see how much did the robot move forward, or rather how much did the image move backward, right? And so the way to do that is to look for features. If you're in the middle of an ocean, you yourself, if you're in the middle of an ocean, you have no idea whether you've gone forward or backwards, left, or, you know, there's no way, and assume it's daytime.
Unless you can
right?
see the land, the coast.
Unless you see a feature, that's right. Unless you can see a feature upon which you can kind of gauge. So we do this intuitively. Scan matching is the algorithm that uses those 2 images to give you that. Now, for a simple case where you just go exactly forward, that's easy. But when you start adding in rotations, it becomes very, very complicated very fast. And you've got
There's
this
a lot of
cursor.
noise too.
Yeah, and a lot of noise.
Understanding what's noise and what's not is a big problem.
Yeah, huge problem.
Wow.
Hardware failures, man, I had my share of those with this thing. You know, something's not working. It's typically a connector or wire loose somewhere. It's, you know, overheating. that was fun. I actually
What was
had
overheating?
flames.
The motor drivers?
A motor yes, a motor
Control.
driver that I was using was too cheap.
Right.
So it actually literally burst into flames and I had to blow on it. The whole house is stinking like that electrical. Yeah. Wife wasn't happy about that. And yeah, this is all the future work that I'm hoping to do with this. The coolest one, in my opinion, is going to be visual odometry. If I can train something to take the LiDAR readings and be able to tell how far I've gone forward and be able to match that with images that are coming into the RGB camera. It's kind of like an auto-supervised learning algorithm, is because the LiDAR can tell you how far away you are, and then the neural net that would be the deep net that would be observing the cameras would be able to, adjust its weights according to that. So that would be kind of a cool thing to do. So yes.
Do you have an IMU?
Yes, it does have an IMU. In fact, that board is pretty cool. It's got an IMU, accelerometer. It does the gyro for angular velocity, and then it's got a barometer, a thermometer, a magnetometer, like all sorts of cool stuff on there. So yeah, in fact, the IMU I use for the calibration of the LiDAR and the motors themselves, just to know which way I'm spinning. If because initially when I hooked it up, the USBs came in at different numbers. Like one was TTY USB 0, one was 1, and I didn't know which motor was which and which one was spinning which way. So I just wrote a calibration script using the external IMU to be able to tell, okay, when I tell it to go right, is it actually going right? And is the angular velocity, indicating a turn to the right or to the left? So yeah, definitely a good thing to have. And for SLAM algorithms, those are invaluable.
So what is under motion planning? What is BWA?
So these are you can read about these on ROS actually.
Okay. Are you using ROS or?
I am not.
You're not.
We work with ROS at work, but I wanted to implement these algorithms myself. Like I said, I just wanted to get a deeper understanding of them, and I figured implementing them would be the best way to do that. DWA stands for Dynamic Window Approach. It's a short-term motion planning algorithm, which explores certain possibilities and picks one. SBPL is a more long-term motion planning algorithm. It's called Search-Based Planning Library. That's all. Both of those are available in ROS, as is AMCL, the Additive Monte Carlo Localization Algorithm, which you can use for SLAM.
Okay.
All available on ROS. Very easy to hook up to it.
So what's the last one?
The A-star algorithm is sort of the basic, like an A-star graph search, of grids that you can do, like Dijkstra's graph node search. It's kind of the precursor to everything else as far as motion planning is going. If you want to go from point A to point B, which using a graph and costs, which is the most efficient path to take.
Yeah, you have to have a map and you have to have a known position and an endpoint. Find it there.
Cool.
So, that's the presentation. Any questions before I do the demo?
So last time you had a cell phone app, right?
I did. I was
Yeah.
going to do it on the browser so that everybody can see.
Oh, okay.
Yeah.
Do you have an iPhone or an Android phone?
This is an iPhone, but
Okay.
you don't. It's not an app actually. It's browser.
Just the browser.
Just the browser. You can
Oh.
fire up your browser either on your laptop or your
because
phone.
You're using
or
Jace.
you're using HTML5 for 3D rendering. Yeah. So
That's cool.
everyone has heard of the demo effect, right?
Tell us.
The demo effect is
It
whenever.
won't work. Yeah.
That's right. That's right. So let me see what the IP address of this thing is, because I got a little script that kind of emails me whenever it's,
Blue screen of death.
All right, let's see. Hopefully it was able to connect to this Wi-Fi. I actually brought it in one day just to make sure. Yeah, the day I showed it to you, Miguel. Yeah. Come on. Just need an IP. Now it's my phone. Wi-Fi here is working, right? Everyone got Wi-Fi?
Well, there is a Wi-Fi network for RoboLink. I just don't know the password.
I think it's
Rolling point.
yeah. All right, I'm gonna try it on my laptop. Give me one moment.
Any capitals?
No, all lowercase.
I don't know why the policies are in Spanish. I don't understand the privacy policy, man. Okay. So 192, 168, 1.5. Someone remember that?
162, 198, what?
What? No, don't mess me up, man.
198.5.
168, 1.58.
192, 168, 1.5.
192. Oh, I can't do it in that window. Okay. Let me bring up another window.
It says the password for RoboLink is incorrect.
Okay. There we go. 192, 168, 1.58.
I thought it was 5. What did you say?
No, it's 58. All right, cool. So here we are. Where's my mouse? Actually, let me grab my mouse real quick. It's easier with the mouse than the trackpad. So yeah, look at the screen and watch as I go past. Watch. You can see my feet. Those two little dots.
If you say so.
Yeah, it's a little hard to see, but hopefully as it starts moving, you guys will be able to. Okay. So the center is this dot, and this is the back. So let's go somewhere. You can see the circle here of the. This is the range of the LiDAR, right? Over here. And as you go forward, if you look at the scan, you can see it. And I was able to. Yeah, it's the machine is much faster than the LiDAR. So you can see there's the door, right? And now the door's on our right. And that is the whiteboard or easel, or I don't know what you call it, but yeah. And now the door's on our right.
So that's actually the door and the door frame, right?
Yes, correct.
the
This is the
indication.
door frame right here, and
Right.
this is the door.
Okay.
Correct. Yeah, it's definitely not intuitive until you start getting used to it, right? So now we're facing this obstacle.
So it truncates the values to some max, is that why you end up seeing the circle?
Correct. That is the outer range. Yes, the outer range of the LiDAR. So I can drive it straight with this mouse while looking at it. Nope. So yeah, these are raw scans, as you can see. Hopefully in the future I will be able to show you like an actual map. Let me see if I
So the moving dots, is that just due to noise, or?
Yes, the moving dots, so the way that it works is that it sends out a beam and it reads back time of flight for that particular beam as it's spinning, right? And different surfaces have different properties when it comes to light. And for example, black shoes will absorb a lot more of the IR than, a white shirt.
Uh-huh.
And as a result, you're going to get beams that bounce off a certain way, and the time is going to be slightly different because it's so sensitive to that.
Mm-hmm.
But for the most part, LiDAR is king in terms of sensors.
Mm-hmm.
What happens if it sees a mirror?
Then it sees whatever distances the mirror is reflecting. So for example, if I had a mirror on the ground, and I had a LiDAR pointing directly down at that mirror, it would measure the distance from the ceiling to the LiDAR.
Yeah, it typically looks like a hole. Like,
Yeah.
It's like a portable hole, you just put that around and robot sees a hole.
So anyway, that's my demo.
We
What's
use
up?
that for cliff detection. test
Wouldn't it
cliff
be possible for
detection.
the robots LiDAR detection to bounce back and hit itself so that it sees itself in the mirror? And
Yes, in fact it probably does. See the LiDAR plane itself for that particular tiny slice. But everything behind the LiDAR is what the mirror would show, because it would hit those, get back to the mirror, come back to the LiDAR,
You know, that would essentially be the same as the sensor picking up a LiDAR from another robot, so it kind of makes me wonder.
Yeah, there does happen. If there was another one that was mounted at the exact same plane, there would be crosstalk between them.
Yeah.
And they would get confused. You would start seeing ghosts, hallucinations. You know, it's a problem. You know, yeah, it's definitely a real problem. So.
If you had a very expensive LiDAR, would that image look quite good, or is it just the
Yes, so for more expensive LiDARs, first of all, it would update a lot faster than what you're seeing right now. It would look almost, you know, like 15, I don't know, however many, hundreds of times per second. And second, you would see a higher resolution. You notice, you know, the space between these two, you know, you can get LiDARs that are like 1/10 of a degree, you know, very, very accurate, but those are like $800.
The problems are still the same though. Like you see like some things are blinking in and out, and you get kind of like noisy data, you're still gonna get that. Unless you were just like in a perfect white room with perfect corners and nothing crazy to bounce off of.
Yeah.
The other thing that's kind of interesting with IR is that it's not always what you can see that matters.
Do you know how to do like a middle click on a Mac?
Middle
So
click.
You pointed out
Let me
a thing,
see.
you think maybe
I think that's
really well.
usually 2-finger click.
I thought that was right click.
Try different materials to make
Mm.
it
That's the right click.
Okay, well in that case, like the settings can kind of be changed. In that case, maybe it's
Okay.
like a control click.
Control click? Like a command click, you think?
Yeah.
Where's my mouse? I don't even see my mouse. There it is.
That's
So
the right
command
click,
click?
too.
Nope.
Try a control click.
Control click? No, that's right as well.
Let me see. Try shift click. No, alt. Try alt.
Alright. Z click. Nope. Shift click. Yeah. If for some reason my middle button doesn't work, but that's kind of the way that I would be able to use to
Maybe try
change this angle.
Try a 3-finger click. See if that works. No.
No.
Okay, so go to the settings. Maybe you have to put it in. I mean, maybe you have to set that up.
Okay. Preferences. Any other thoughts, questions? Oh, it doesn't even have a middle click. Okay, that's why. Okay. So yeah, if you were on your phone and you would, in fact, whoever wants, if you're on the Wi-Fi here, you could probably bring it up.
School avoidance, or it's just that?
Ultrasonic.
You want to bring it up, Dylan?
Yeah, try.
Just put in the IP address.
Yeah, put in the IP address, and you guys can compete.
What type of? Okay. Cool.
And then if you click on, if you tap on one finger and then use the other, you can actually move the plane. And it's kind of a, I don't know if you guys can see. Whoa! Who's doing that?
That would be me.
Alright. Don't break my robot, man.
Sorry, I can't. I don't know how to use this thing.
You just move forward. If you swipe up, it goes up. If you swipe back, it goes back.
Okay.
That's it.
I think I'm starting to get this.
There you go. Any other thoughts, suggestions, comments? What's up?
How do
This
you
is pretty cool.
factor in people, like, and you worry the robots for your work, how do you?
Yes, that would be motion detection within the what we would call the perception stack. So remember when I was talking to you about scan matching, right? You can scan match and then do a difference between two images when you're fairly confident of your scan, right? So if you know that with a very high degree of probability that your robot moved up 2 steps, then you can take those 2 scans, subtract them together, and see what pixels are different. And the pixels that are different are the pixels that are moving with respect to you, right? They're not the stationary pixels that are in your environment. They're actually moving things. And then then it becomes a matter of, okay, what are these 2 pixels? Are they 2 feet? Are they whatever? And typically anything that moves you want to avoid. So.
Also, we have a lot more sensors than just LiDAR on the stuff that we do.
Yeah, that's a good question.
You gonna integrate your visual sensors, you said?
I want to. Unfortunately, on this board, I probably won't be able to do a live stream, but I might be able to record video, and then based on that, be able to create a map with like plastered, picture snapshots. I don't know. I hope, you know, once I get, but it is possible to be able to do that.
So you don't have enough horsepower is what you're saying?
To do live streaming, no, because the GPU doesn't have the drivers for JPEG encoding, hardware JPEG encoding. If it did, then no problem. Like the Raspberry Pi does, but if, yeah, unfortunately not.
So any thoughts on upgrading
Upgrading?
your?
No, I actually, you're hitting
That's
right. No, I mean, I hope to be able to apply the lessons learned with this and also the code base to some of the other projects that I work on, namely the PVC Power Chair that Dylan hosts, which I'm very proud to be a part of. I mean, if we can do something like that for the wheelchair where you can press a button, you know, and it takes you from one known location to another, avoiding obstacles, that would be fantastic, I think. You know, so with a basic LiDAR, I mean, one of the things that, for example, I would change about this design right now is that I would actually bring the LiDAR lower. I would probably, you know, because it'll hit things and you know, like David wouldn't have been able to see a lot of things that are underneath it. You want the planar LiDAR as close to the ground as possible so that it picks up obstacles that it can comfortably go over, which is not the case in this case, right? So.
You just seen another one.
Yeah, yeah, exactly. So no plans right now. I mean, I've got my hands full learning all these algorithms, lots of scientific papers, lots of heavy math, lots of you know, researching and trial and error. But
Is this WebGL? Is that what you're using?
I am not actually pure HTML5 canvas. Yeah, this guy wrote a JavaScript library for it, and yeah, no WebGL, which I was very impressed by.
Sorry.
So if you wanted to build a map with this data, like what would you?
So for example, if I wanted to, like the next talk, which I hope to have in about 6 weeks, would be, we drop the robot here, and then we would manually drive it. Maybe even David can do it again. We'd manually drive it around, and it would collect these samples as it goes, and as time progresses and as it's going around the environment, it would build a full map of what it sees. And it can actually spit out a nice map that you would be able to explore, just like you are right now with the raw scans. And the map would look like this. It would look like, you know, just lines, right? It's kind of an overhead view of what the map
Are there
is.
like common like data structure standards for like how those maps are built and stored?
Well, it depends on what you're doing. You can represent it as a sparse graph, or you can represent it as a very dense matrix, you know, which is the entire map. I mean, it depends on how much horsepower you have and what you want to do with the map.
Yeah.
So, there are definitely things that lend themselves more naturally to this kind of representation. Like for example, poses. Almost everybody uses X, Y, and theta, right, to represent the pose of a robot. And I'm no exception, right? The heading and
Depending
X
on
and
how
Y.
many degrees of freedom you need.
Yeah.
So
If you had a drone, yeah, you would have.
Like if you have a drone, for instance, your representation of what that data looks like, it's probably going to be very different than if you have a ground project.
Right. I'm just wondering if like, you know, are there maps that you can kind of pick up from other
I see what you're
people
saying.
and like
Yeah,
you know,
I mean, I'm sure. Yeah.
but like with raw kind of like stay out of like the raw kind of format, you know?
Yeah.
That's not like
I mean,
yeah.
the way most of those kind of like toolkits work is that there's a whole bunch of different ones written by a whole bunch of different people and not necessarily compatible,
Yeah.
but you can use any of them. Like MRPT is another example of where you can get involved in algorithms.
Having fun, David.
So they're all.
Yeah, I was just trying to get the hang of piloting this thing. It's
Online for you.
I couldn't see what the heck I was doing when it was over there, so.
Gotcha.
It's the fringes where you really have to spend the time.
And you could always convert maps, Dylan.
Yeah. Yeah.
You know, from one format to the next. The data is simple, you know, just millimeters from one end to the other.
Right.
So yeah, you would potentially be able to drop things in. Yeah, so, but essentially it would be, you would train a map, right?
Well, it's like in our connected future, like it'll be like
Yes.
the map data will be
Yes.
you know, ubiquitous
Yes.
in a way.
And I'm sure there will be lots of converters between this map, and like this app and that app.
What's the durability of the LiDAR, and if it went into a commercial product, would you have to enclose it in a transparent case?
So the way that the Nito, which is a commercial product, did it, was that they had a bit of a plastic enclosure that would,
Have an open slot in the front?
yes, so it would be a thin slot just over here, like this whole thing would be covered, and all it had was this thin slot. And for them, they actually didn't need the whole 360, so they actually limited it to like, I don't know, probably maybe 270, maybe 280 degrees, and then they just blacked out this thing, right? And they just had, just for protection. And then they had a couple of pillars as well, which I think they used for calibration. You know, because the LiDAR would always hit them, and they would know based on where those three things were in relation to the LiDAR, they could tell which way the robot was actually headed relative to the scan.
So it's belt drive and it's got brush contacts to power the lasers that are spinning, or? Is it
Yes, I do believe that it's got a, what are they called?
commutator ring or something?
No, there's a ring.
Slip ring?
Slip ring. Yeah, I think it's a slip ring that's in there. I haven't actually taken it apart.
There are a couple like similar form factor LiDARs that are available now that are kind of Kickstarter level.
Oh.
You can buy for $200.
Yeah.
Okay. Just wondering about durability and if it hits bumps and stuff.
It's actually pretty good. I mean, it looks like a pretty flimsy belt in my opinion, but man, this thing, I've had it for like 6 months, and it's been running a lot. I mean, I develop on the board itself directly. I don't have cross compilers just yet set up. So, no, every time that I turn it on to even write some code, it'll just sit there and it'll run. So, yeah, it looks flimsy, but it's actually more durable, especially if you keep it covered and clean. I'm sure it'll last a long time. The LiDAR itself actually has an encoder, but the power that I get out of that Arduino Mega is so clean that I don't really need the encoder to be able to do the PID on the controller to make sure that it's spinning at a constant rate. But that motor that spins the LiDAR does have an encoder, so if you had a motor controller, you could control the LiDAR very, very, very precisely and make sure that it always was at 300 RPM or 289 or whatever you wanted, right?
Would that give you higher resolution or?
No, it would just give you higher fidelity, like you would know for a fact that this is, but like I said, I look at that scan and I don't see a difference, you know, which.
It's pretty good.
Yeah, I mean, it's.
Yeah.
Right, yeah,
Yeah.
so, I ended up skipping that part because it would be a bit of work and more hardware. Yeah. So navigation, autonomous navigation is the goal. Anyway.
Cool.
You're gonna
Anybody
make
else?
the mapping algorithm so that it's adaptive, so that if, it doesn't think there's a wall there, but then it runs into a wall, it has to update the.
Well, the
mapping.
idea is that it won't run into a wall, right? Because the LiDAR will see the wall.
Yeah.
And so it'll put the obstacle there.
When you're taking samples, you're
Yeah.
taking them over time, right?
Mhm.
So you're sort of generating a probability of a wall over time.
Yeah.
So you take a scan of a wall, you may not see it this scan, but the next scan you might see more of a wall.
But if you have
The
a
next
black
scan you might
wall,
see more.
Yes,
kind of
that's a problem.
generating-
yeah.
Yeah.
Yes, that's a
You
problem.
know what I mean?
The-
Like,
you know,
more
vision
and more
is
of a
king.
probability that
right?
there's a wall.
You can
over
figure
time.
out vision. That is the ultimate, right?
But you have to be
Does
able
this
to
have
combine
navigation around an
those
obstacle
scans
yet, or you
together.
have to have it?
Yeah.
I don't have any navigation on there. I don't even have a slam going on. This was just like, here is the platform, here's the scan, here's like all this code that I wrote for the firmware,
Yeah,
the motor
I mean,
controllers, the LiDAR scan,
answer
all of that
is,
stuff.
it's
I'm
not that
just
easy.
starting on the LiDAR scan matching, you know.
Often it's like.
But
some
yeah, in
algorithms
about
just try
6
to
weeks,
filter
I'm
out
hoping to
some
have
bad object.
just the mapping, which is,
More
and then
sensors.
in another 6
You know
weeks,
what I mean?
I'm hoping to have the motion planning, which would be the autonomous obstacle avoidance, sort of algorithms that I mentioned, like SPPL, DWA,
And
all
you're
that
gonna
stuff.
use the stereo cameras for that, you think?
No, no. Stereo cameras will be a long-term, future kind. Once I've got it stable enough where I can trust that I can build a map reliably,
Mhm.
then I'll be able to match what I'm getting out of the cameras with what I'm expecting from the LiDAR, right? So that I can say to the cameras or to some vision, algorithm, neural net, deep net or whatever, that is exactly 200 millimeters away, and run the deep net training on it to say, when I see this box, I will say that it's 200 millimeters away, or this feature. And that way I'm hoping to be able to train a visual odometry algorithm that can be hopefully trustworthy. That's my idea, being able to train visual odometry, because that would be, especially at a slow speed, that would be awesome, I think.
What about adding ultrasonic sensors? And-
I have not had good luck with ultrasound.
Okay.
I think that I don't know, it's not as high fidelity, nearly as much as LiDAR. LiDAR, you know, is like one notch below vision, you know. So right now, the most trusted sensor in any robotic, I think, I don't know if you guys agree, I mean, is
you
LiDAR.
can do full autonomy with just the
LiDAR, you know. That is, you know, speed of light isn't changing, so.
yeah, it's not maybe
the balancing.
Yeah,
like
it's
you
not
might-
perfect.
You might
but
want a couple LiDARs or something like that.
to have redundant sources and,
Yeah.
yeah.
Play around with different angles of them and things like that.
Well, thanks, guys. I appreciate it. Thank you for listening and checking it out. I hope we have something a little more impressive next time. So,
All right.